Hello, welcome back to everybody. So, last time we were doing something which was a model of a very simple CPU. Actually, not really a CPU, not already, but what is called Arithmetic Logic Unit. So, we had this circuit here. We said that somehow we can interpret this AND gate as a multiplicator between two operands A and B, and similarly this XOR exclusive OR gate, here you have the schematic diagram of this symbol and the corresponding truth table. We interpret it as a summation between the two operands A and B. Then we had two extra AND gates, this one and this one, operating in the so-called gating mode, so the modality for which when you activate one input, which comes from this operational input here, so if this is activated, so whatever is here passes at the output, and similarly for this one. But there is a NOT gate, so this AND gate, when this AND gate is activated, this other one is deactivated and vice versa. So the the operation input number 3 here selects the results of the multiplication or either the summation to go here. And then we need just the OR gate in order to merge the result with one possibility, which is a zero output, which occurs when the AND gate in the gating modality is not activated. And finally we have the result. So we have a little machine here that calculates two different operations, and we can select which one we want to have as the results. You can imagine that you can make this thing much more complicated. You can probably replace this circuit with something that will calculate the multiplications not only of two 1-bit numbers, but with two numbers having a number of bits which is bigger than this. Then there are also more complicated things, because for instance in electronics we have this representation of numbers which are also called floating numbers. So they have a so-called mantissa and exponent. So in a way they divide the decimal part from let's say the order of magnitude of the number, and many other more complicated things. But this is just to give us an idea of how in principle an arithmetic logic unit might work. So now we can take all this stuff and we can put it together in a paradigm which is called CPU, the Central Processing Unit, which is the basics for the digital computation. Let's say not the basis, but one possible basis, so one possible way of doing computation. Okay, so let's try to go into this. So again, this is a model. So modern CPUs are not done this way. I mean, this is too basic, but still, I mean, it can give you an idea. So now what we have, let's describe those blocks. We have a block which we call CK, which is a clock source. So if you remember, we had this oscillator we called clock oscillator. So a circuit that can produce an alternate signal, square wave, with some periodicity that we can program. So now by setting two values of those two components. So why do we need this? Imagine we attach a clock to a counter. So this type of circuit here, we have seen that if we attach a clock to the first flip-flop and they are all connected in chains like this, then the outputs will represent a binary counting. So this thing in the jargon of the CPUs is called the program counter. Now we also know that we can do something else. We can produce electronic circuits according to a given truth table. So imagine you have a circuit like this. Okay, we still have the nodes. That for a given, let's say, configuration of inputs, so if you see A, B, and C, if you put the time here, this can be the result of our program counter. So it's a counting 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. So for each time instant which is indicated by one of those rows, this circuit will produce one output that we can decide what it is by deciding how the circuit is done. So let's imagine now that we have a similar circuit but with 3 outputs. We said that we can do this. We can create a function from, let's say, binary n to binary m, where n is the number of inputs, now the bits of the program counter, and m is the number of outputs. We just need to replicate this circuit many times, m times. So if we stick to our model of CPU, 2-bit CPU, so if we have that those 3 things are the outputs of an hypothetical combinational circuit, then it means that by scanning the truth table of that circuit by means of a program counter, we can produce a sequence of operands and operations that can be fed to an arithmetic logic unit in order to produce a result. But a sequence, a temporal sequence of operands and operations is a program. So it basically means that this hypothetical circuit, combinational circuit, is the place where this program is stored. In this case, it would be a so-called ROM, read-only memory. So we select which is the line of the program we want by waiting for the program counter to reach an appropriate configuration, and this configuration is communicated to our let's say truth table by means of those signals, which collectively are called address bus, and this would produce data that go into the arithmetic logic unit, and then we have the result according to a sequence. So this paradigm has been invented in the past. It has been studied by several scientists, and it's the same paradigm we have here basically in every computer we have, from the smallest one like the microprocessor in this thing here, to the microprocessor which is inside the guts of this tablet, computers or whatever. So everything is still working with this paradigm. So this is how computer can compute. So what's the rest in computers? of course, bigger number of bits, more operations, complicated stuff, because this thing is a read-only memory, but we might want to put our result back into another memory in order to retrieve it later for other usage. So beyond any sort of implementation of a read-only memory, there is also a random access memory, or called RAM, RAM, which nowadays basically is implemented as an array of capacitors. So the RAM nowadays it's an array of capacitors. Every bit of the RAM is a capacitor that you can charge, and then you read the value. If you want to set it to 0, you discharge it. If you want to set it to 1, you charge it. And those capacitors are implemented into the silicon chip. There is a possibility of doing a capacitor directly in silicon, and they are very, very small, very, very integrated, so the RAM can be very, very big in a very small chip. And also because it's small, it's also very fast. So this is also an advantage of making things small in electronics. They become very, very fast, and they consume less. So it's an advantage to try to integrate things in a small area. Okay, so now before switching to another topic, I want to do one thing that I think it would be useful, preparatory, let's say, also for the new topic. So I did this. So it's a calculation I've done a long time ago when I was a student attending a course of something, let's say, digital electronics, the CPU design, and such kind of things. So in electronics, we have logic gates, and or not, combination of gates, whatever. So you can imagine that if you want to connect things like here, I mean, you can easily have very complicated circuits, connections, many things. So you have physically to go from one point to another one with the wiring, I mean, the routing of your circuit. And despite the fact that the circuits are very integrated, I mean, still you have a distance to cover with your signal along all those wires. So in the microchips, I mean silicon, there is this thing, the dominant components at the fundamental level, even inside the diodes and the transistors, are of two types, resistive and capacitive. So we don't have so many inductors. It means that the magnetic field in a microchip is very small. And this makes a dramatic change in what is called the propagation time for the signals. So if we have a sort of balance between the strength of the magnetic field and the electric field, we have a propagation in terms of waves, like electromagnetic waves, let's say radio signals, or light in the extreme case. So for those kind of signals, we have a wave equation. We have mentioned this when we were speaking about electromagnetic waves at the very beginning of the course. So what I'm speaking of is this thing, basically. Where is it? Okay, speaking about this. So in this kind of situation, we have that the signal is propagating, let's say, from a source to a target, and it takes a certain amount of time, which is proportional to the distance. So, simply speaking, the farther you want to send a signal, the more the time you need to do this. But in the microchips, we don't have this behavior. We have something different. We have a process of let's say propagation of signal, which is called diffusion, and this makes the time of propagation to be much bigger. So it's a constant, so it's proportional not to the distance but to the square of the distance. It happens like this. So it has to do with the fact that there are very little inductances and mainly only capacitors. And so let's see what happens. Now we have a path with a certain length, so the total path between A and C is x, and then we want to send a signal from A to C directly. So according to this, the propagation timing is kx squared. But let's now to break this path in two parts, and we put a node here. When we put let's say a repeater, an amplifier, so instead of going directly from A to C, we go from A to B, and then we have a repeater in B, and from B to C. So for instance, a repeater for us can be two NOT gates, one after the other one. We know that not something is like as you did nothing, but the signal is regenerated because inside the gates there are amplifiers and whatever. So let's compute the timing, the information travel from A to B according to this diffusion timing equation, where the distance is not x but the half of x. So TAB is k multiplied the distance x divided by 2 squared, so is k x squared divided by 4. And similarly, if then the signal is regenerated in B and sent to C, because we have the same half distance here, the time TBC is the same, is k multiplied the distance x half raised to the square, so it's k x squared divided by 4. And now the strange thing that happens, that if you put together the two timing, so the timing for the signal propagating from A to B and then from B to C after it has been regenerated in B, so this time is the summation of those two, and so it's k x squared divided by 2, which oddly, but it's like this, it's smaller than the time for going directly from A to C. So the strange result is that when you have a propagation timing for which the law of propagation is according to a physics related to diffusion and not to waves, if you put an extra node in a path, so if you break the path in two, then the total timing of propagation is reduced, in this case by a factor of 1/2. So this is something that is strange, but it happens, and it's used a lot in electronics in order to speed up signals. So because we have this diffusion conditions inside the propagation of signals in silicon, if you want to send a signal very far and fast, you can speed up the signal by breaking the path and putting relays that basically regenerate the signal. So if you add extra nodes, instead of slowing the signal, you speed it up. Okay, so let's try now to completely switch topic, but we will see that there is a strong connection between what we have done so far and what we will try to do now. Let's try to speak of neural networks. Okay, so here we don't speak about all the physiologies. You have much better and deep courses for this, but let's try to just have a, let's say, an idea of what's going on. So here we have a schematic diagram, a representation of a neuron, one type of neurons, let's say. There is a body here, and here there is a sort of channel pattern, it's called the axon. So this cell, now we don't say how, let's say that it can produce, receive and produce electric inputs, and the signal can travel from one place to another one, which, let's say, quite interesting, but also complicated electrochemical signaling. I mean, it's not so easy, but for us, we take this as a black box, and we consider that a biological neuron is something that can emit pulses which are similar to this one. They have a sort of stereotypical shape. So if I measure the voltage of those pulses, and by measuring the voltage I mean the membrane voltage, so if we have a ground somewhere in our place where we have these neurons, then we measure the membrane voltage respect to that ground, and it turns to be that those pulses that can travel along the axons and reach other neurons are something like this. So they have a voltage from top to bottom of about let's say 100 millivolts, in that order of magnitude, and the duration of those pulses are in the order of milliseconds, just a few milliseconds, so 2-3 milliseconds, and the pulses are like this. This is the only thing that say the neuron can do: generate a pulse like this or receive a pulse like this from other neurons. So those two persons here, McCullock and Pitts, try to describe this situation from the point of view of the information. So they were not interested in the shape of this pulse, the timing, but just on the fact that this pulse can be present or not at a certain time instant. So if we consider this model, we can associate a digital meaning to these pulse trains. So here we have a representation of what a neuron can emit or receive, for instance, in terms of sequence of pulses. Where you have the 1, it means you have the pulse. So here you have in this chart, let's say, a spike. And when you have a 0, you don't have the pulse. So for us, the information is conveyed in this system as a train of pulses. And here comes the idea: how can we describe the behavior of a neuron? There are several ways, but this model, which is probably the simplest that exists, is still quite successful, and it has the advantage of being very simple, so it can be easily understood. So it's done this way. we have a so-called summation node where many signals like this can arrive, and they are summated according, summated together according to a weight. So it corresponds to this situation here. This value S is the output of this summation node. The weights are coefficients that gives importance or remove importance from an input. So if you put a weight to 0, then basically that input is not considered. Let's say if you put the weight to 1, then you are taking this input, but you can put the weights having different values. Then the output of this first stage, the summation node, passes through another black box here, which is called the threshold. So the threshold is a system that evaluates if the value of S is above or below a certain threshold T that you can set. And according to this, you have a binary output which we call Y, which is 0 if the variable S, the summation, is below the threshold, and 1 if the summation is above the threshold.